All right, so in Chapter 2, what we're going to do is turn our attention from looking at the Earth as a whole, like we kind of did in Chapter 1, and talk about these processes that occur on Earth that have changed the Earth throughout the billions of years that the Earth has been around. The Earth is about 4.5 billion years old, a little bit older than that. Life on Earth occurred or began about 1 billion years after that, but there was a lot of going on Earth that kind of set the stage for life to actually survive on Earth. Early Earth was a very different place than it is now. It was actually not a very conducive place for life. And so we know now, especially with our understanding of geology and this plate tectonics that we're going to talk about in this chapter, we know a lot about the Earth in terms of its dynamic processes. The Earth is a very dynamic place. It's changed quite a bit. Even if we can't see the change occurs relatively slowly. We can look back through the geological record, and understand that there's a considerable difference between what we see on planet Earth today, how it looks, the arrangement of the continents, and the way it looked many years ago, millions or billions of years ago. The ocean floor is a really interesting place. It's oftentimes said that we actually know more about the surface of the moon than we actually do about the floor of the world's oceans. We have been down to the ocean floor in some cases. You see on the left-hand side, this is actually a picture of diving down into one of the deeper parts of the ocean. One of the biggest problems with going down there, of course, is the pressure involved. Water exerts a pressure of somewhere in the vicinity of about 16 pounds per square inch for every 30 feet of depth. So when you get down to the bottom of, like, say, the Challenger depth, or Challenger deep, which is on the order of 35,000 or so feet, you can do the math. You can find out very quickly that the pressures are incredible. And we used to think that there wasn't anything living down there, that nothing could stand that kind of pressure. But as we've explored those areas of the ocean, we found out that there's quite a few organisms that survive down there. What's neat in the picture that you see that I just drew the arrow to is if you look at that viewing port, that glass, you notice that it's broke, right? And that's because of the immense pressure. And in some of these submersibles, especially like one of the first ones, or at least the first one that went into the Challenger Jeep, the Bathyscaphe Trieste, the glass, if I remember correctly, my reading was somewhere on the order of 3 to 4 inches thick. So that's an incredible amount of pressure. But notice, there's a fish living there, right? There's a number of living organisms that live on the bottom of the ocean. And we'll talk in later chapters about how those organisms have adapted to survive with those kind of pressures. Now, it's not only the pressure that's an issue down there. It's very cold. It's very dark. And there's nothing to eat in the sense of organisms that produce food. In biology or in ecology, when we talk about producers, we're talking about the plants, so the organisms that actually can photosynthesize. Well, at this depth and pressure, of course, with no light, I mean, it's pitch black all the time, there's no light down there, so there's obviously no producers. So a lot of the organisms that live down there survive simply by either eating each other or this, what we call a nutrient rain. So it's basically organisms that dying up near the surface, falling down through the depths and decomposing as they go through, and that nutrient rains down to the bottom of the ocean, and that provides sustenance for a lot of these critters. What you're looking at on the right-hand side, and we'll see a bigger picture of this as we move into this chapter, is the Atlantic Ocean. I'm sure you recognize that. Obviously, there's Florida over here and Africa. This line right down the middle, that line is called the Mid-Atlantic Ridge, and we did not know about the Mid-Atlantic Ridge until really about the middle part of the century, until sonar became used prevalent. Sonar use was prevalent. Sonar, which is an acronym for sound, navigation, and ranging, is, and I'm sure you guys are probably familiar, or you've seen this on movies involving submarines. Sonar basically works by sending out a pulse of sound, and then that sound bounces, like if you were to yell an echo, yell against a cliff, and that sound then bounces off of structures on the bottom of the ocean, and structures that are taller, the sound will be returned quicker, and substances that are or structures that are closer to the ocean floor, the sound will take a little longer. So we can get a three-dimensional picture of the way the ocean floor looks. Well, man, I tell you, when oceanographers discovered this mid-Atlantic ridge, it really was exciting because it confirmed a lot of the hypotheses and ideas that early investigators had proposed about how the Earth had come about and where the continents are. Now, back in 1912, a guy named Alfred Wegener, there he is on the right-hand side, smoking a very interesting-looking pipe there, came up with this idea called the continental drift model. Now, in science, a model is basically the way we think something looks or the way we think something works. We're all very familiar here in Florida with hurricanes. So during hurricane season, they'll often have tracking models of hurricanes. And it's those spaghetti, they call them the spaghetti models, where all those different colored lines showing where the hurricane may go. And the reason why we call those models, again, is we've gathered evidence throughout time about the normal track and path of a hurricane, and we can build predictions out of that. So that's what we mean by model, the way we think something looks or the way we think something works. Alfred Wegener first proposed his theory of continental drift back in 1912 and then published it later on in a book known as The Origin of Continents and Oceans back in 1915. At the time, he suggested that what was going on is the continents, North America, Asia, Africa, and all that sort of stuff, were actually plowing their way through the ocean basins. So they were moving. Now, where this came from was actually, Wegener wasn't the first one, but a guy named Francis Bacon, Sir Francis Bacon actually, was one of the first credited with kind of noticing that if you look at the eastern coast of South America and the western coast of Africa, and again, I'm not much of an artist, but you get the idea, they sort of fit together like a puzzle piece. It looks like they may have been together at one time. Now, we know that that's the case, but at the time, while that evidence seemed to suggest a puzzle piece fitting kind of arrangement, we certainly didn't understand the mechanism. So Alfred Wegener came up with this first mechanism, which was the continents being pushed through the ocean basins. And this was not well received by the scientific community. For example, what Wegener was proposing was actually defied the laws of physics. He also suggested that another mechanism that may have been moving the continents was the gravitational attractions, the tidal gravitational attractions. Now, we'll talk about tides later on in the semester, but of course, living in Florida, there's high tides and low tides. By a combination of the gravitational attraction of the sun and the moon. And Wegener suggested that perhaps that's what been responsible, or at least partially responsible, for moving these continents around. But the amount of force, amount of gravitational force exerted on planet Earth from the moon and the sun was too small. It could certainly cause the bulging of the water that causes the tides in the ocean. So it certainly could have some attraction on the oceans, and it does. But to suggest that could somehow move these heavy continental plates around was beyond what we understood, was beyond science, was beyond a reasonable expectation. So while Wegener had the right idea, the idea that the continents were drifting, that they were moving, and again, that comes from just a very simple observation of how they fit together, but he had the wrong mechanism, and that's not unusual in science. Science many times is like an onion. The ideas of science are built layer upon layer. So many times what happens in science is an investigator will propose an idea behind how something works, but not necessarily have the mechanism right. Darwin, for example, there's Charles Darwin in the picture. He had the right idea about evolution. Now, Darwin wasn't the first person to talk about evolution. Lots of folks before Darwin had discussed it. But reason why we hear probably more about Darwin than anybody else is Darwin had the correct mechanism. Other folks had proposed this idea of evolution, organisms changing through time, but they didn't have the mechanism right. So now Darwin had the correct mechanism. But just like anything else in science, as I said, with this whole idea of layer upon layer upon layer, he didn't completely understand how the mechanism works. See, Charles Darwin didn't have quite the understanding of genetics that we do today. So that is, I guess, the one of the what do you want to call it? One of the sad things about science, I don't know if that's the great word for it, is the idea that oftentimes you may propose a model about how something works or how it looks, and you may have part of it right, but because of a lack of understanding of some other aspects of science, you can't exactly say how that worked. And oftentimes these folks, like Charles Darwin, die and never really worked out exactly the way this mechanism of natural selection that Darwin was proposing. So it's kind of the same thing with Wegener. He had the right idea about continental drift, but the mechanism behind it he was wrong on. It wasn't these continents plowing through the ocean basins, or it wasn't anything to do with the tidal attraction of the moon and the sun. It was actually something called plate tectonics. That was the mechanism. So let's kind of investigate this a little bit further. First, let's take a look at where we believe the continents started from. When land masses arose on Earth, when we had this terrestrial, when we had dry land, we think that the first continent that formed, the first major continent, was this one, Pangaea. And as you can see in the picture there, Pangaea is all the continents together, right? We have North America, South America, and there's what there's what Francis Bacon had looked at, right? See that fit between those two? It's a pretty close fit if you think about it. So about 175 million years ago, or I'm sorry, Pangaea existed about 200 million years ago, but about 175 million years after that, Pangaea began to break up. It began to move away from one another. At that time, there was only one continent and one very large ocean called Panthalasia, which included an ancient sea that we call the Tethys Sea, which is now, of course, the Mediterranean. You can see where it is. But notice how this all fits together like a puzzle piece. Now, when Wegener was proposing his theory, one of the criticisms that the scientific community laid upon him was that the fit wasn't exactly right. So there was this idea of, are you seeing something that really isn't there? Well, back in the 60s, they actually used computer modeling, which Wegener wouldn't have had access to, and they plotted the fit not based on where the edge of the continents are in terms of dry land, but using the what we call the continental shelf. So what they did with this computer modeling is they looked at how the fit between the continents occurs if you were looking at where the continents are at about 2,000 meters depth in the ocean, which is the true edge of the continents. The continents don't start right at the beach. The continents actually start a little further offshore, as I said, down to about a depth of 2,000 feet. And then, or 2,000 meters, excuse me. And then, of course, you have the ocean floor beyond that. So if we look at the true edge of the continents, the part that's in the black there, the little line, we see that the fit is a lot better than even Wegener and those other folks were looking at. All right, we have some evidence to suggest that this indeed did happen, that there was a Pangaea and that eventually it broke up. For example, one of the things that we can look at is the mountain chains, matching in mountain chains. So if we look at Pangaea as a continent together in this picture on the top, if you bring the continents together, the Appalachian mountain range on the eastern part of North America matches up very nicely when these pieces are put together with, I believe that's the Ural Mountains in Europe. So there's this this idea of when the continents come back together, we have this continuous mountain chain. The picture down here, similar sort of evidence here. What we're doing is looking at rock assemblages, and rocks, even though rocks kind of all look alike to many of us, to geologists, they're substantially different from one another. So when we look at these assemblages of different types of rocks, and if we put the continents back together into that large supercontinent of Pangaea, we notice, like, for example, if you look in equatorial Africa, this rock assemblage right here, we find very similar rock assemblage on the eastern coast of South America. So you see these puzzle pieces are fitting together. One of the other things that gives us evidence outside the geological range is looking at the distribution of fossils. And one of the best examples of that is a very interesting fish that's still around today. Extant, by the way, folks, is the opposite of extinct. So if we look at the present distribution of organisms, extant organisms like the lungfish, we find some very interesting clues into this whole idea of continental drift. Now, it's just not with lungfish. As you can see in the picture down below, we have fossil evidence from some other dinosaur era organisms, dinosaurs. And what we're looking at in the colors there is their fossil distribution across the continents. And notice, for example, in this critter down here, the fossil distribution is throughout South America and then extends across to Africa. Now, the only way we could really reasonably explain that happening is if those continents were together at one time. And you can see there are other similar examples in there as well, including some plants. But back to the lungfish for a second. Present-day lungfish occur in South America, Africa, Australia, and there are some fossil lungfish that are found on the continent of Antarctica. I'm sure you all are aware that Antarctica is very different than the Arctic. The Arctic, there is no continent in the Arctic. It's ice floating on the ocean, whereas Antarctica is actually a continent covered in ice. Well, lungfish, they don't really have lungs the way you and I have lungs, but they have a respiratory organ that allows them to breathe outside of water. So that's a relatively very specialized organism. So when we think about in science explaining things like that, we could say, all right, those lungfish in South America, Africa, Australia, the ones that were fossilized in Antarctica, they all independently came up with this very specialized respiratory organ. But in science, we always want to pay heed to this concept of parsimony. And parsimony says that basically the simplest answer is usually the right one. So if we look at the present-day distribution of lungfish, this very specialized critter, it's less parsimonious. In other words, it's less likely that these lungfish in these different continents today all evolved a similar, very specialized respiratory organ independent of one another. The better explanation, the one that makes more sense, and the one that fossil evidence has actually supported throughout the years, was that when the continents were all together, lungfish actually lived in all of these regions. Let me get rid of my scribble here for a second. So lungfish distribution actually occurred throughout South America, Africa, Antarctica, and Australia. And then as the continents moved away, the lungfish that were in those different continents drifted with them as well. So we get evidence from the geological realm with the rock assemblages. We have evidence from the biological or the paleontological realm. Glacial flows too. The way glaciers flow, move over ground, they actually leave scars. If you've ever been to New York City, in Central Park, there are these huge outcrops of granite. And if you look at those outcrops of granite, they actually have striations in them, or scars, if you will. So this is an outcrop of granite. We see these parallel lines. And what that comes from is as glaciers move over the bedrock, they oftentimes have pieces of debris and rocks and stuff trapped in the ice. And those pieces of debris will actually scour these lines into the rock. If you've been to New York City and to Central Park, you may have seen this before. And if you don't, if you ever get a chance to go up there, do by all means venture off into Central Park and look at some of these rocks. It's really kind of interesting to notice. But the direction at which those rocks scouring, the direction in which those grooves that are carved moves, gives us also indication of a connectedness or of a Pangea existence. So the rock scouring moves between continents. So for example, if we were looking at rocks that were scoured by glaciers between Africa and South America, we might suggest that since the lines are similar across the continents, that they were together at one time. All right? Okay, now, this whole idea of plate tectonics. Plate tectonics is the mechanism, right? Continental drift is the result, is the theory. That's what we see. What moves the continents is this idea of plate tectonics. And again, as I mentioned before, a lot of this has to do with the advent of sonar, which really didn't come around until World War II. And just after World War I, sonar began to be developed, but it actually reached sufficient enough sophistication for us to be able to do seafloor studies World War II and afterwards. And that's what I was saying earlier about discovering that mid-Atlantic ridge. So we're able to see the bottom using sonar. We also have some evidence of how plate tectonic works and the movement of the continents by looking at the Earth's magnetic field. For example, this rock over here, magnetite. When rocks form, right, from lava or magma, when they cool off and form rocks, if it's a rock that has magnetic crystals or magnetic particles in it, like magnetite does, those crystals will line up based on the arrangement of the North and South Pole. So we can actually see, where the North Pole was at the time that these rocks formed. So as the rocks cool, those crystals stay in the same arrangement. So once the rock is cool, whatever way the magnetic field of the Earth aligned those crystals, it stays that way. Well, you might be thinking, what do you mean about the North Pole and the South Pole? Haven't the North Pole always been in the north and the South Pole always been in the south? Well, not exactly. The poles have actually wandered through time. Folks who study this study something called paleomagnetism. Paleo means old, folks, like paleontology, folks who would be studying the dinosaurs and stuff. So in paleomagnetism, what we're doing is we're studying the Earth's ancient magnetic field. The Earth has a magnetic field because in the interior of the Earth is an iron core that is spinning around, and the spinning of that iron core in the center of the Earth actually creates this magnetic field. The North Pole and the South Pole, the North Pole, isn't just a place where Santa lives. It's actually a magnetic place, a magnetic phenomena. When you hold a compass up, the compass doesn't point to the geographic North Pole. It actually points to the magnetic North Pole. They're not necessarily one and the same. Depending on where you are on the planet, your magnetic North Pole is going to be off from the geographic North Pole. It's what we call a declination, compass declination. And declination is the difference in angle between the geographic North Pole and the magnetic North Pole. Paleomagnetism has also showed us, like you see in the picture on the right, that the magnetic North Pole has moved through time. Even in recent time, it's moved, right? In 1831, the magnetic North Pole. Now, again, how do we know all this? By looking at those rocks during the time that they were formed. The magnetic North Pole was much further south in 1831 than it is in recent times. So the poles have moved. Now, how does this give us evidence about plate tectonics? Well, if we look at the Earth and we bring together this evidence of where the North Poles were, we come up with this discrepancy. Look at the map on the left first. So the part that's in the black is the polar wandering, the movement of the North Pole, over 300 million years, as you see in the picture there, for the Eurasian continent, and then in the part in the red is the apparent polar wanderings for rocks that are formed in the North American continent. So if you look at rocks in Eurasia, they point to the polar wanderings that you see along the black line, and the rocks in North America point to the polar wanderings you see on the red line. Well, you can't have two North Poles, right? You can only have one magnetic North Pole. So there's a gap between here. They don't line up. But they only don't line up if you assume the continents are in the position they are today. If we go back and we assume that the continents were together as Pangaea, as these ancient continents, then the lines line up. All right, so we have like fossil evidence, rock assemblages, the scouring of glacial rocks, the placement of the poles. All of this tends to point to this idea that at one time the continents, as Wegener proposed, were together in this one giant supercontinent that we call Pangaea. The poles have also reversed through time. About every 250,000 years, the North Pole becomes the South Pole becomes the North Pole. Again, not geographic, but magnetic. And in the past 76 million years, there's been 176 reversals. Now, what's interesting about that, well, first of all, when I was a kid, everybody was all up in arms about the polar shift, and if the poles were to shift, the world would just go into chaos. It's not quite. It's not quite as dramatic as a lot of these books that when I was a kid were very popular for folks to read, and among other things to worry about being hit by an asteroid or the poles shifting. But one of the really neat things that the polar reversals have done for us is provide us another piece of evidence for this idea of these continents drifting and moving. This is the mid-ocean ridge, and for example, this like the mid-Atlantic ridge that I showed you. And what's happening here in the mid-ocean ridge, or specifically the mid-Atlantic ridge, is that molten material, raw rock material, is moving to the surface, and it's basically forming rock on the bottom of the ocean on the surface. And whenever that rock is formed, whenever it cools from the magma to the solid rock, whatever way the poles were at that particular time, those crystals in those magnetic rocks will show that. So when we look at it, we find that throughout time, we see that there's a reversal of poles. So in the darker regions is when the Earth's magnetic pole was normal, so it was pointing the way it is now. And in the bluer regions is when the pole was facing the other way. Polar reversals. Now, notice something interesting about the way this picture is. It's symmetrical, right? See, these match up. What that indicates to somebody looking at this, and the model we use to propose this, is the reason why we have these parallel symmetrical lines on either side of the ridge is because as the rock moves forward, the ridge, or the rocks, move away from the ridge in opposite directions. All right, so there's this idea that as molten material solidifies in the rock, it's pushing the continents away from one another. So Wegener thought it was gravitational attractions, or he thought that the continents were plowing through the ocean floor. It wasn't really that at all. It was more a matter of rocks being formed, or earth material being formed at these ridges, and as it's formed, it's pushing the ridges apart. Now, if you go back, well, we don't have to go back, we can go forward. This is the mid-Atlantic ridge again. If that's occurring, then the rocks that are forming, or the ridge, is pushing the continents away from one another. When we age rocks, and there are ways to age rocks using radiometric decay, using radioisotopes like uranium is used sometimes. It's similar to the way, well, precisely the same way that you use carbon-14 dating. Now, you can't use carbon-14 dating on rocks because carbon-14 dating is only good back for, I think, about 150,000 years or something like that. And these rocks are on the order of millions or billions of years. But notice, you can see what looks like, obviously, a spreading that's occurring, but notice the symmetry. Right? Notice the symmetry of the age of the rocks. The further you get away from the ridges, and there's another one over here called the East Pacific Rise. The difference between a ridge and a rise, a ridge is sharper. The Mid-Atlantic Ridge is the sharper sort of, actually, if I draw it on both sides like that, because this is where the rock material is coming up. And a rise is shallower. It's not as sharp. Right? So again, we're pushing away from this side. Regardless of whether it's a ridge or a rise, you can see if we look at the age of the rocks, there's a symmetrical spread of the age of the rocks. So again, more evidence to suggest that the plates are moving away from one another. Well, if the plates are moving away from one another, if we're building up rock material along these ridges and these rises, there's got to be a place for the rocks to go, or the Earth would get bigger. And it's not getting bigger, right? The Earth size is staying the same since the Earth came into being. So where does the rock go? Well, if we look at evidence from earthquakes, occur predominantly. Many of the earthquakes occur along the western rim of the Pacific Ocean. This whole area right around here is called the Ring of Fire because of the prevalence of all the earthquakes. So here's the Mid-Atlantic Ridge, and there are some earthquakes along the Mid-Atlantic Ridge, but what we really see is a majority of the earthquakes occurring over here in the western part of the Pacific. Of course, we all know that there's earthquakes out there in California, earthquakes along the western coast of South America. This is where the rocks, this is where the crust that's being formed at the Mid-Atlantic Ridge or at the Pacific Rise that we have there are diving back down into the earth. All right, so this is the surface of the earth. The rocks move apart from one another, and then when they get, like, say, to the western part of the Pacific, this is where the trenches are found. Like, this is, remember, where the Challenger Deep was found, or the Marianas Trench is the name of the trench. So as the rocks move apart, they eventually dive back down into the interior of the earth where they're remelted. So we got a lot of evidence to suggest that indeed these crust of the earth is moving apart from one another. Now, basically, the construction of the earth is, we have that iron core that I talked about, and then we have the layer down below, the molten rock, and then at the very edge, this very thin crustal layer kind of rides on top of this rock, or of this molten rock. So we have all these plates, kind of, if you imagine an egg, and the eggshell is broken up into a bunch of little pieces, but it's still on the egg. That's kind of the way the Earth looks. It's like with a bunch of plates all on the surface of it, and they're all banging up against each other, and they're moving apart at the mid-Atlantic ridges and the rises. And when they crash into one another, because that's pushing that way, that pushes that way, so they're going to meet over in this area. Then they actually dive down into the depths of the earth and be formed back into magma or liquid rock. Okay. So this is a picture that kind of shows what we're talking about. The crust that I've been referring to is called the lithosphere. Litho means rock, and the sphere is obviously the sphere of the earth. And we say the lithosphere, the crust, floats on top of something called the asthenosphere. And the asthenosphere is the semi-molten layer of rock. So this here would be the lithosphere, right? And all of this down here, where the mantle is found, would be the asthenosphere. So the heat flow. So what happens is the heat flows up to these areas where the ridges, and the heat flow can be up to 8 times higher at the ridges than it is in other areas of the asthenosphere. So what happens here is rock moves to the surface at the ridges, like I've been saying, okay, spreads apart. Now, this kind of makes sense, right? If you're pushing material up into this ridge, that means in order to make room for more material, this ridge has got to move apart. And then when it gets to the other side, the rock or the lithosphere then dives down beneath another piece of the crust. And oftentimes what happens is we say that the pieces of the oceanic crust, or parts of the oceanic crust, will dive down below pieces of the continental crust. So this would be the continent. And then this stuff moves down back into the mantle, where it's remelted, and then eventually is recycled back up to the surface. That's why scientists are always so interested when they find really old rocks. Like some of the oldest rocks are found in Australia and Greenland in the order of about 3.5 billion years. And if you think, well, I thought all rocks were old. Well, if rocks are constantly being recycled like this, then we're not going to have a lot of the old rocks around. They've been subducted. That's what it's called. There it is, subduction zone. That's what it's called when the lithosphere dives down into the mantle. So these rocks are actually being recycled. But the old rocks in Greenland and Australia that I've been talking about, that geologists get fascinated with and excited about, those rocks haven't undergone subduction. They are rocks that were around since basically the beginning of the Earth, in many cases. So pretty close, 1 billion years, give or take a few. Now, what happens oftentimes around these subduction zones is we get volcanoes. And sometimes it's called a volcanic arc because it basically follows right along the trenches. There's the trench. So that's what the Marianas Trench or the Challenger Deep is. It's a subduction trench. So you got 2 plates pushing against each other, and one many times dives below the other. So it's like this conveyor belt of material. So here's another picture of it, right? We get material moving to the surface at the ridge, and we have material diving down back into the mantle. And what's causing all this to occur is something called ridge push. So ridge push is actually just the deposition of more and more rock which causes it to spread out. And then on either end, we have something called slab pull. Slab pull means that as the crust that's being subducted, and again, subducted means you're diving beneath another piece. So the part in the green there is being subducted between the part in the orange that you see. As that piece subducts down, the weight of the slab continues to pull the rest of the slab with it. So that's the mechanism that's moving it. So we got ridge push, pushing the rock apart, or the crust apart. We have slab pull, pulling the crust down. And then there's also something called slab suction. This is what I'm trying to illustrate with slab suction. Slab suction is basically the same physical process that occurs in your sink drain. You know, as water's running down the drain, if you were to put your hand over this drain, you would feel a suction, right? You would feel a force pulling the rest of the water down. So as the lithosphere subducts down into the asthenosphere, down into the mantle, we get the weight of the slab pulling it down, and we also get this suction that occurs that pulls it down. So you got pulling here, pushing here. So slab pull plus slab suction is greater than ridge push. So that means that there's going to be a net flow of the crust moving apart from one another. Now, what happens when those two plates come into contact with one another? All right, well, three things can occur. For example, or what happens at the junction of plates? Three things can happen. If it's the plates moving away from each other, we call it a divergent plate boundary. Right? This is what's happening at the mid-Atlantic ridge. Rock material is coming up, and the plates are moving away. When two plates come against one another, one can die below the other. So this is what we call a convergent plate boundary. And we say this one right here is being subducted. The plate on the right is being subducted underneath the plate on the left. And a lot of times at convergent boundaries, you get those very deep, focused times of earthquakes. Divergent boundaries, like along the mid-Atlantic ridge, can have earthquakes, but as you remember in that ring of fire picture, tend to be a lot less frequent, and they tend to be more shallower, so higher up in the earth. Deep are earthquakes that occur down, way down into the depths of the earth. Plates can also move across each other in a I was going to say an up and down fashion, but it's not an up and down. Look at it like that. One plate's moving this way, the other plate's moving this way. We get a transform fault. Now, these are the ones that cause the earthquakes, which can be particularly problematic because they're usually very strong and very shallow. See, the deeper an earthquake is, the less shaking occurs on the surface because a lot of that energy is absorbed by the earth before that force or that shaking force makes its way to the actual surface. But in a transform fault, we have two plates moving side by side, and of course they're rocks and they don't slide very well past each other. They stick. Well, they're still being pushed by that plate tectonics mechanism. So eventually what happens in these areas where they stick, they break loose, and that's where we get the earthquake. And this is what's happening out in California. This is what the San Andreas fault is, a transform fault. And here we get shallow, very strong earthquakes. So those are particularly traumatic for habitation, obviously, because it's a strong earthquake that occurs very high up in the earth. It's not down in the depths. Well, here's an example of a divergent boundary once again. So the Mid-Atlantic Ridge is a divergent boundary, right? We got material moving away from one another, so the plates are moving to either side as material forms. You can see a really cool picture. This is on the pictures in Iceland. Iceland is one of the neat places on Earth where you can actually see this divergent boundary, this Mid-Atlantic Ridge on the surface. The Mid-Atlantic Ridge, of course, is down at the bottom of the ocean, but in Iceland it actually makes its way to the surface, and this right here is the Mid-Atlantic Ridge. It's huge, too, because that little thing in the circle is a bust to give you some idea of scale, so just to get an idea how big that is. So what we got occurring here is material moving to the surface and spreading out. And it's confluent, or it matches up perfectly, that ridge in Iceland with the Mid-Atlantic Ridge. Iceland's about right there. Now, Now, if you think about what's going on, when these plates are diverging from one another, you can form an ocean that way, right? Because if you think about it, here we go. We start at the top. So we have this material moving up. You know, it's physics. You got more material being deposited here. Something has to get out of the way. So the plates move apart. Eventually they form what's called a rift valley. And then that rift valley can actually fill with water. First, it makes what we call a linear sea. And the good example of a linear sea is this one right here, the Red Sea. A linear sea, it's sort of a long, you know, line-shaped sea, if you will. And then eventually, like we see in the Atlantic Ocean, those plates continue to move apart, fill up with water, and we get the ocean. So the Atlantic Ocean is getting wider as this ridge moves apart, and conversely, the Pacific Ocean is getting narrower, right? Okay, so again, ridges and rises. Ridges and rises, basically the same thing is happening there. You have this upflow of material from the asthenosphere coming to the lithosphere and pushing those boundaries apart. And as I mentioned before, a rise, like for example in the Eastern Pacific, right here's the Eastern Pacific rise. Rises, the spreading that occurs at a rise tends to be faster. The slope is more gentle, and there's a much less distinct rift valley. Now, this is what I mean by a rift valley. If this is material moving up, then we get this pileup of rocks this way and this way. So on a rise, this rift valley is going to be a lot shallower, a lot less distinct. So it might be something like that. Whereas in a ridge, the rift valley is going to be a lot deeper. Oceanic rises or rises tend to move a little faster. For example, the one in the Eastern Pacific moves at about 16.5 centimeters a year, so you're talking 6 inches a year. So even though the Atlantic Ocean is getting wider and the Pacific is getting narrower, it's not getting narrower or wider real fast. The oceanic ridge is a lot slower. The one in the mid-Atlantic moves apart at about 1 inch a year, so 2.5 centimeters a year. So Europe and North America getting farther apart by about 1 inch a year. The rift valley that occurs in the mid-Atlantic ridge in some cases can be 2 kilometers deep, 20 kilometers wide, and these ridges on either side can actually rise up to a height, form these mountains somewhere in the vicinity like 3,000 meters tall. So that's a pretty significant oceanic structure. And again, we didn't realize this even occurred until we had sonar. So you can imagine looking at it on a sonar, people just blown away by this. And again, like I was saying about Iceland, here's Iceland again. You can see the ridge actually is at the surface in Iceland. All the little red triangles are volcanoes. Iceland is a very volcanically active area. So what's happening at the mid-Atlantic ridge? The North American plate moves that way, the Eurasian plate moves that way, and material is bubbling up, if you will, or being forced up from the asthenosphere and forming along that ridge line. So the Earth's a pretty, like I said, pretty dynamic place. There's a good picture of the mid-Atlantic ridge, right? So all of this is moving across. Now, all of these fracture lines that you see is because a ridge, a more or less straight line, is pushing plates across a circular surface. The Earth is a circular surface, a spherical surface. And the combination of those two causes those breaks that you see in between. But nonetheless, plates are moving apart, and then here's Iceland way up here at the north. So if we could drain the oceans and look at the Atlantic, the mid-Atlantic ridge would be one of the most prominent features that we would see on the surface of the Earth. All right, here they are coming together, convergence. At the place where we get convergence, what happens depends a lot on the density of the plates that are meeting. For example, at convergence boundaries, we get volcanic or island or continental arcs, as I said, strong earthquakes, and it's the density that decides which plate dives or subducts beneath the other. For example, if it's an oceanic plate and a continental plate, crust, the oceanic crust is denser than the continental crust, so the oceanic crust subducts, and this forms trenches. And it also forms continental arches, or continental arcs. Continental arcs are as the oceanic crust dives below and is heated up, the pressure that builds from the heat actually causes some of that material to rise to the surface in mountains and also in volcanoes. If it's the oceanic crust meeting another piece of the oceanic crust, well, then it's going to depend on which one is the most dense between those two, and the more dense one is going to dive below. Typically, the one that dives below that's most dense is going to be the older one. And we get trenches there, and since it's two oceanic crustal plates, we're not going to get a continental arc, but we get island arcs. And it works the same way. Instead of forming a volcano on land, it forms these volcanoes out at sea. And of course, here's the surface of the ocean. Here's the land. As a volcano forms and gets bigger and bigger, it eventually moves through the top of the surface, and we get an island. If it's two continental plates of equal density, neither one of them subducts. So what happens here is if you were taking a piece of paper and pushing on it this way, and then that paper is up against a wall, the paper would actually buckle, right, as you pushed on it. So what you get is a buckling, and the buckling forms mountain ranges. So you can see here's the continental crust, another piece of continental crust. Neither one subducts below the other one, but they run up against each other and cause this warping or this formation of these mountain ranges. Okay, so it's all about density here. And the depth of the trench is proportional to how far away the trench is from the spreading center. So that's why the trenches in the western part of the Pacific are so deep, because they're quite a ways away from where the crust is spreading, the mid-Atlantic ridge or also the eastern Pacific rise. An oceanic and a continental convergence. All right, an example of that would be along the western coast of the United States. So let's go back, oceanic and continental. We're looking at what occurs here. So we get trenches and we get continental arcs. And continental arcs can form volcanoes, as I said. And we all know on the western coast of the United States, there's quite a few volcanoes. Mount Baker, Mount Rainier, Mount St. Helens. This is Mount St. Helens going off back in, was it May of 1980, if I remember correctly. And the reason why we have this chain of volcanoes moving down through the Cascade Mountains is because the Juan de Fuca plate, which is moving this way, is subducting between the North American plate. There's the subduction zone. And as it dives down below and that rock gets heated up, things that are hotter are less dense than things that are cooler. So the hotter rock is going to rise to the surface and eventually can make its way up and form a volcano. So volcanoes like Mount St. Helens are the evidence that we've got a subducting plate diving down below a continental plate and being heated up that way. And if you've ever seen videos of the eruption of Mount St. Helens, it was pretty dramatic. Mount St. Helens, here it was, after the volcanic eruption, basically it blew the whole side of the mountain away. Just devastated the landscape too. Major eruption. I was actually up in Seattle soon after Mount St. Helens went up. My parents were living up in Seattle at the time, and I was living in California. So as I drove south from Seattle to California, it was like volcanic ash it was like snow. It had rained down. There was volcanic ash covering all over the place in this part of Washington. Mount Rainier is another volcano. Now, a lot of these volcanoes, some of them are active, Mount St. Helens, some are dormant, and some are extinct. I think if I remember right, the volcanoes on the western coast here, I'm not sure there's any extinct ones, but these are either dormant or active volcanoes. An example of an oceanic convergence, so two oceanic plates coming against one another. And again, in this case, it's going to be a matter of which one is more dense than the other. And oftentimes what they do is they actually, when they push against each other, they force each other down or form a trench. The Puerto Rican Trench, off in the Caribbean, is an example of an oceanic convergence. Puerto Rican Trench, I don't know how deep it is. It's not as deep as the Marianas Trench, But there's a plate here, and then this is the Caribbean plate. And then they move against each other, and they're actually forming that ridge that forces it down. A continental convergence, a good example of that is India. Early on in the formation of the continents, when Pangaea broke up 175 or so million years ago, if this is the Asian continent, India actually, which is kind of a triangular shape, India migrated through, very slowly of course, moved through the Indian Ocean until it finally ran into the Asian continent, to that plate that forms the Asian continent. And since they're both continental plates, one didn't subduct between the other one, but it formed a buckle, and that buckle is the Himalayan mountains. Right, so here's an ocean ridge, and that's where the plate would be formed. That's where the crustal material is formed, moving north, running into the Asian plate, and eventually forcing up. Just like I said, if you were pushing a piece of paper, it would wrinkle up in the middle. There's Mount Everest, as a matter of fact. Beautiful place. Love to see Mount Everest one day. Mount Everest is an order about 29,000 feet tall, getting taller, by the way. So if you plan on climbing any part in the Himalayas, you sooner rather than later is a good idea, because they're growing at about 1 centimeter a year, so a little less than ½ an inch a year. All right, transform faults. Out on the western coast of the United States, there it is, the San Andreas Fault. We got the Pacific plate moving in this direction, the North American plate moving in this direction, so two plates like I drew moving side by side in opposite directions. The plates stick, and eventually they break apart. So the movement of the plates is perpendicular to the mid-Atlantic, to the mid-ocean ridges, not moving left to right, if you will, relatively speaking, but moving apart one another. Not very fast. The San Andreas fault moves at about 5 centimeters a year, but the plates stick together, and then eventually they break loose, and the breaking loose is the earthquake. The spreading that you see and the transform or the fracture zone faults, the lines that run this way, so this is the ridge. It has to do again with a linear ridge spreading out on a spherical planet. Okay, and so we get these two things, this massive amount of material, these two plates rubbing against each other with a lot of friction, a lot of storative energy, and eventually it all breaks loose at one time. The plates slip, and that's an earthquake. We get these very strong, shallow earthquakes. And for human beings, as I said, that's some of the worst, obviously, because they're strong and they're very shallow, so they can cause a lot of problems. Transform plates or transform faults can occur either between oceanic plates or continental plates, or oceanic and continental plates, depending on which way the plates are moving. So they're not going to be subducting necessarily, because subduction would occur because by them moving against one another, towards one another, where these are moving in opposite directions from one another. Let me skip this slide for a second and come back to it. This is a picture or an illustration of the Pacific Ocean near the Hawaiian Islands. This is Hawaii down here. Let me get a better color than blue and blue. Here we go. This is the Hawaiian Islands down here. And the Hawaiian Islands is called an archipelago. An archipelago, it's an I. An archipelago is a group of islands. Oftentimes, an archipelago is named something islands, so it's the Hawaiian Islands. You know, there's many islands in Hawaii. There's Hawaii, Oahu, Molokai, Maui, Kauai, a bunch of different islands. And if we took away the water, we would notice that the Hawaiian Islands are more than just the stuff on the surface, that the Hawaiian Island archipelago actually includes all the islands down here on the surface, but all these other these oceanic islands, if you will. They're not above the surface, or oceanic mountains, maybe you could call them. They're below the surface. But notice how they're moving. It looks like there's a directional, there's a line to it. And when people were studying the bottom of the ocean, they noticed that, and they said, that's kind of interesting. I wonder what's happening here. Well, the Pacific plate, which is what Hawaii rides on, the Pacific plate is moving in a direction basically kind of off to the northwest. And where Hawaii is in present day, there's actually a shallow spot, a thinning area between the lithosphere and the asthenosphere. So now I go back to that previous picture. So it's a hot spot right here. So here's what I say about the Pacific Plate. There's the Hawaiian Islands moving off to the northwest. When we date the rocks in the Hawaiian Islands, we find out that the rocks that make up the islands further out are older, 3.8 to 5.6 million years, whereas Hawaii is only about 700,000 years old. So that means that Kauai was formed before Oahu, Oahu before Molokai, Molokai before Maui, and Maui before Hawaii. What's going on here? Well, this is called a mantle plume, or a hot spot, or a nemataph. Nemataph is the plate is moving over this shallow hot spot area, this relatively shallow area, and because it's thinner at this spot, the mantle plume, the heat from above, is bubbling up and forming these islands. So if I could kind of look from above now, so as the plate moves over that shallow spot, material bubbles up to the surface and forms an island. So the reason why the Hawaiian Islands have the shape they do, kind of off in that direction, and then the rest of those islands, is because, and down here you can see it better, is because the plate is moving in that direction. Another really good piece of evidence for this movement of the plates and the plate tectonics. Right? So a hot spot, or a nemataph, is a thinning of the lithosphere, and at that thinning of the lithosphere causes volcanic activity to occur. See, this mantle plume is bubbling up, right, forming a warping, and then eventually bubbles up to the surface. And if the plate is moving in this direction, you can follow the way the plate's moving by looking at the track of the islands and dating them. Right, so these are older up here in the northwest. These are going to be older and gradually getting younger as we move down. Now the hot spot's right there, and the plate's moving this way. So the plate's moving over the top of the hot spot, and every time it does, material bubbles up, if you will, forms up from the mantle and forms the islands that we see there. Coral reefs and volcanoes. Interesting relationship between those two as well. So again, we have the idea that material is bubbling up beneath the surface of the ocean, and as that material bubbles up, it forms an island. I remember as a kid in science class, we actually saw an old video. It was off near Iceland, if I remember right, where wrong color. There we go. Where we have the surface of the ocean, we have the ocean floor. A sub-oceanic volcano starts depositing material, rock material, and eventually that breaks its way through the surface and forms an island. What was neat about that I saw was the fact that, in spite of the fact that this island was formed basically out in the middle of the ocean, within a very short period of time, within just about a year or so, vegetation started to show up there, and then animals. So in spite of the fact that of its remote location, it doesn't take very long for life to gather a foothold on these places. So if we look on the left-hand side, starting on the left, we have what's called a fringing coral reef. Now, the significance of the coral idea is coral needs relatively shallow water. So coral is not going to form at the bottom of the ocean. Coral is not going to form in deep depths. Coral is an animal, but it actually lives in a what we call a symbiotic relationship. Symbiotic relationships, I think we've talked about that before, are relationships between two organisms. They can be mutualistic, where they help each other. Parasitism is a symbiotic relationship. Now, in that case, only one gets helped, and the host obviously gets hurt. But coral lives in a symbiotic relationship with an organism that photosynthesizes. The animal coral provides a place for this photosynthesizing organism to live, and then the photosynthesizing organism provides food. Right? So the volcano forms, we get a fringing coral reef. If that volcano then goes extinct, so this is a lot what's happening in Hawaii, because of course, let me go back again. As the Hawaiian Islands are moving over this spot, the hot spot's right here. So as these islands have moved off away from the hotspot, there's not going to be any more volcanic activity. Well, erosion begins to occur, and the volcano begins to decompose, and we get a barrier reef. Right? So the barrier reef is the coral that was at one time around the volcano. And as that volcano eventually rose to the point where it's subsurface now, so if we could look below the surface, the volcano is the dashed line below the surface there, we have what's called an atoll. And an atoll is a barrier reef with a lagoon in the middle of it. Atolls are usually, well, they're typically very easy to see. Diego Garcia, which is an island out in the middle of the Indian Ocean, is an example of an atoll. See, this is the all surrounded by coral. So there was a volcano in the middle at one time, and that decomposed eventually to the point where all we're left with is this deep water lagoon, typically pretty deep in the middle, and then the barrier reef on the outside. Australia is interesting too. The Great Barrier Reef, which occurs off the northeastern coast of Australia, is one of the pristine premier diving sites in the world. About 2,000 kilometers long, 150 kilometers wide. Incredible species diversity. But from a plate tectonics point of view, the reason why the Great Barrier Reef is so interesting is because it gives us another idea of the movement of the plates. You see, the Australian continent sits on a plate that is moving north. Coral, as I said, needs shallow water, but they also need warm water. They don't do as well in colder water. We have a coral reef in this state in Florida, down around the Florida Keys. But you don't find coral up off New York or even on the western coast, because water on the west coast off California is much cooler. The reefs grow thicker and more plentiful in warmer water and thinner in colder water. So if we look at the Great Barrier Reef, the reef at the northern end is thicker, and the rocks, if we date around the reef, are about 30 million years old. And as we make our way south, the reef becomes thinner and younger. It's only about 10 million years old. Well, the only way we can explain this is if the Australian continent sits on a plate that's moving north towards the equator, right? So the equator's up in here. So as the Australian plate moves north, this Great Barrier Reef material moving north with it enters into warmer and warmer water, and that's how it grows in thickness. So we are looking at the thickness of the coral reef, the lushness of the coral reef, as well as the age of the coral reef. So this part up here that was 30 million years old was eventually down here further south and made its way north. So we got a lot of really direct evidence showing us that the plates have moved. You know, Hawaii moving over the hot spot, Australia and the coral reef, you know, which leads maybe to the final question, what's it going to be like in the future? So if we look at about 50 million years from now, 50 million years later, again, there's the Mid-Atlantic Ridge, pushing the plates apart, the Eastern Pacific Ridge. There's also a ridge here. Remember what I said, the crust, the lithosphere, is like a bunch of parts of an eggshell that's broken up in little pieces, riding on top of the asthenosphere, that liquid part. And you can see, you know, they're not moving apart very quickly. So in 50 million years, North America and the North American plate will be a little bit further west. So Florida will have moved from about where it is to, say, where present day, I don't know, Mexico is. South America will have moved a little bit further away. Over there in Africa, it's not moving quite as fast. And of course, as we just mentioned, Australia is moving north. And India is moving north, causing the Himalayas to rise. Now, millions and millions of years after that, we would expect that these two plates would meet, right? Or I'm sorry, these two continents would meet, North America and Asia. So Pacific is getting narrower, and the Atlantic's getting wider, a little bit at a time. All right. So continental drift is a well-accepted theory, in spite of the fact that Wegener got all the ridicule at the very beginning. We begin to accept the fact that he was probably he was right. But even though he didn't quite understand the mechanism, you remember first he said he thought it was just the continents were plowing through the oceans, or in conjunction with the gravitational attraction of the sun and the moon. It's not that at all. It's simply a matter of rock being formed down below in the asthenosphere, coming up to the surface of the ridge and then pushing apart, which is causing these plates to move. And then at the other end of the plates, they dive down below each other, and that material is recycled. So it's constantly being recycled. So that's why, again, when they find old rocks, like up in Greenland and Australia, they're very geologists are fascinated by that sort of stuff, because most of the rocks have been recycled. And one of the things we can do with those old rocks is oftentimes when rocks form, they trap little air bubbles inside of them. So if we can sample the rock and actually sample the gas that's trapped in that air bubble, we can get an idea of what the atmosphere was like at the time when that rock formed. And that's what gives us an idea of what the early Earth's atmosphere was like. For example, the early Earth's atmosphere had very little oxygen in it, very little of any oxygen. It was mostly methane, ammonia, hydrogen sulfide, a lot of hydrogen sulfide especially, a lot of gases and methane that you come out of volcanoes. So this paleoclimatologist, people who study ancient climates, can use these little trapped air bubbles to get an idea of what the atmosphere and the conditions were like on the early Earth. All right? So if you're thinking of traveling to Europe, you should probably get your ticket now, because as the ocean gets wider, the distance increases, and it's going to cost you more to fly there. Of course, if you wait a little bit longer, then it'll be cheaper to fly to Asia, because of the fact that the Pacific Ocean is going to get narrower. Okay, so that's all I want to talk about in Chapter 2.